In this video, we are studying chapter 4.6, where we take a look at the rank of a matrix and systems of linear equations and how we can find solutions using linear algebra techniques. Our learning objectives for chapter 4.6 are to find the basis for the row space, a basis for the column space, and the rank of a matrix. So we're going to be doing that in the first videos. We're going to look at the basis for the row space and the column space. In the next video, we'll take a look at the rank of a matrix. You're going to see how to find the null space of a matrix and how to find the solution of a consistent system. And another objective is to prove results about subspaces associated with matrices. So given a m by n matrix A, in this section, we will speak of row vectors, which you can see here are the rows divided up into separate vectors. So in this example, the first row A11 through A1n is now a separate vector, through the last row being the mth vector because there are m rows. And then the column vectors, which are corresponding with the columns of the matrix. So we would have n column vectors. So when we look at the column vectors, because there are n column vectors, they each are of length m. So we say the column vectors belong to Rm. The dimension of the rows, because each column is the length of the rows. And then similarly with the row vectors, because the length of the row vectors is the number of columns in the matrix, the row vectors are in Rn, where n is the column dimension. Let's take a look at an example. So here is matrix A. Matrix A is a 2 by 3 matrix. So the row vectors are 0, 1, -1, and -2, 3, 4. Since this is a 2 by 3 matrix, there are 2 row vectors, and then there will be 3 column vectors, 0, -2, 1, 3, and -1, 4, corresponding with the 3 columns. So we would say the column vectors are in R2 because they are 2 dimensions, and the row vectors here, the row vectors, are in R3. Okay, in example 1, just as I said here, note that the row vectors are in Rn, and the column vectors are in Rm. So this leads us to definitions of what are known as row space and column space of a matrix. So the row space of A, where A is this m by n matrix, is the subspace of Rn spanned by the rows of vector A. So in example 1, the row space of that matrix is a subspace spanned by these 2 vectors, 0, 1, -1, and -2, 3, 4. The column space of A is the subspace of Rm spanned by the column vectors. So in terms of our example matrix, the column space here is the subspace of R2 spanned by these 3 vectors, 0, -2, 1, 3, and -1, 4. So recall that 2 matrices are considered row equivalent when one can be obtained from the other by elementary row operations. So the next theorem is going to tell us that row equivalent matrices have the same row space. So theorem 4.13 tells us if an m by n matrix A is row equivalent to an m by n matrix U, then the row space of A is equal to the row space of U. So let's take a look at the proof of this. So because the rows of U can be obtained from the rows of A by elementary row operations, we know we can use scalar multiplication and addition to obtain a row equivalent matrix. It follows that the row vectors of U are linear combinations of the row vectors of A. The row vectors of U lie in the row space of A, and the subspace spanned by the row vectors of U is contained in the row space of A. So that tells us the span of U is contained in the span of A. Since the rows of A can also be obtained from the rows of U by the elementary row operations, right, you could definitely go backwards, the opposite row operations, and go back from A to U. We also have that the subspace spanned by the row vectors of A is contained in the row space of U. So we can also say that span of A is contained in span of U. So because we have containment both directions, and the containment can also be equality, by the way, our containment symbol here has the possibility of being equal, the conclusion we make is that the two row spaces must be equal. Span of U equals span of A. All right, theorem 4.14 is related. It's about the basis for the row space of a matrix. So if a matrix A is row equivalent to matrix U in row echelon form, then the non-zero row vectors of U form a basis for the row space of A. So following the reasoning that we just saw in theorem 4.13, if a matrix U is in row echelon form, then its non-zero row vectors form a linearly independent set. Consequently, they form a basis for the row space of U, and then by theorem 4.13, they also form a basis for the row space of A. So we get this theorem about the basis being able to form a basis for the row space of the row equivalent matrix, as well as theorem 4.13 that tells us the row spaces are equal for row equivalent matrices. So let's take a look at an example here. In our example, we want to show that the non-zero rows of our matrix here, this is a matrix already in row echelon form, are linearly independent. So in order to do that, we have to show that constants multiplied by each row vector, so our constants are C1 through C4, since there's 4 non-zero rows, equal the vector that is the zero vector. So we set this equal to a zero row vector. So the first column on the right-hand side is C1. So C1 is going to equal 0. So if we look over here, here's our C1. And so to get zeros out there, we're going to have to definitely have C1 equal 0. The second column of the right-hand sum is negative 9 C1 plus C2, working from the second column. And that has to equal 0 plus C2, so it must be that C2 equals 0 because we already know C1 is 0. The fourth column on the right-hand side sum is 0, 0 plus C3. Okay, so we know the third column, those are zeros now because C1 and C2 are 0. So the fourth column here, 0, 0 plus C3, because C1 and C2 are both equal to 0. So to get 0 here, the only possibility is if the constant C3 equals 0. And then if we look at the fifth column here, the only possibility is going to be if C4 is 0, because we know C1, C2, and C3 are all zeros. So C4 must also be 0 there if we want to get a sum of 0. So therefore, the only solution to get the 0 vector for this matrix is the trivial solution where C1, C2, C3, and C4 are 0. So then we are able to conclude the non-zero rows are linearly independent. So remember, to show linear independence, we show that the only solution is the trivial solution when all the scalars are 0. Here's an alternate solution. You can take the transpose. So here we had C1 multiplied through by the first row, C2 multiplied through by the second row of the matrix. And so here, if we do the same but convert to columns, and put it in this form, we can see the only way we're going to get a 0 solution here, so now we're working with the transpose matrix over here, is to have all of the constants equal 0. So using this alternate solution, we also get the same trivial solution. The only way that this system will equal the 0 vector is if all of the scalars are 0. So this is just another way of proving linear independence. Okay, in this next example, we are given a matrix and we want to find a basis for the row space. So the first thing we do is we put the matrix in a row echelon form. So here we have a row echelon form of the above matrix. It's not a reduced row echelon form, but you can actually work with either the row echelon form or the reduced row echelon form. And so a basis for the row space corresponds with the non-zero rows. So we have these three vectors corresponding with the first, second, and third rows of the matrix. Those will form a basis. We can ignore the zero rows. And then you could also take the reduced row echelon form. So then you would have the vectors corresponding with the first three rows of the reduced row echelon form. That's another way to obtain a basis. So either method works fine using the row echelon form of the matrix or using the reduced row echelon form. And remember, the difference between row echelon form and reduced row echelon form is that in the reduced row echelon form, the leading entry of each column is a 1, and then each column with a leading 1 has zeros elsewhere. So if you're eyeballing the difference between these two reduced matrices, here in our reduced row echelon form matrix, the columns 2 and 4 have zeros because those are columns with leading 1s. So that's the main significant difference when we go to reduced row echelon form. In this example, we are going to find a basis for the subspace of R3 that's spanned by these three vectors, 1, negative 6, 3, 1, negative 5, 7, and negative 7, 38, negative 37. So my first move here is going to put these into a matrix. So I've got 1, negative 6, 3. In the first row, 1, negative 5, 7. In the second row, and negative 7, 38, and negative 37 in the third row. And then I'm going to put them in row echelon form first, and then we'll look at also reduced row echelon form. So in row echelon form, I've got 1, negative 6, and 3, and then 0, 1, 4, and all zeros in the bottom row. And so in row echelon form, basis I could use for the subspace spanned by these three vectors is 1, negative 6, 3, and 0, 1, 4. I could also work in reduced row echelon form. So instead, if I wanted to take my matrix to reduced row echelon form, where I have zeros in, I'm going to leave a 0 here where I've got the negative 6, that would be 1, 0, 27 in the first row, 0, 1, 4, and that bottom row is still zeros. Then I could use the basis corresponding with these two rows, 1, 0, 27, and 0, 1, and 4. Okay, so we see you can use row echelon form of a matrix or reduced row echelon form of the matrix, either way to find a basis for subspace spanned by a set of vectors that comprise that matrix. So in the next videos, we'll take a look at rank of a matrix.